Thank you, Netra. Screen देख्नु भयो हैन?
Yes, sir, yes.
Yeah, I had a bit of electricity problem. I don't have electricity in my home. I'm using solar power now. Computer लागि पनि मेरो चाहिँ यो इन्टरनेटको लागि solar. I'm using solar power. So throughout this 1.5 hours, I'll use the solar power. I'll not switch over. Anyway, so you said at his seminar 1, last time we have seminar 0 where I try to tell a small part of my life, mathematics, my life. It was an introductory seminar. So now from onwards, it will be a mathematics throughout the ages. So I'll try to tell you about how the mathematics has come up in a historical prospect, not chronically. It will be based on my interest rather than chronicle or real history. So today I have chosen the topic as squaring the circle. So I'll be talking about period from 16th to 18th century, squaring the circle. I will start from a very practical, simple problem which started long time ago, about 16th century ago. So my seminar will be very similar to what I'll be doing today. And I'll be focusing more on historical aspects, how these things originated and how it became a theorem or a part of big mathematics. So that's my aim in conducting this seminar called, which I call, okay, Ganga. Sorry. I call mathematics throughout the ages. So now let's start with my seminar, squaring the circle. So let's look at a very classical geometrical problems. There are 3 problems on geometrical construction. Trisection of an angle, whether we can make a trisection of an angle. So you can see, and doubling the square. It's still not solved problem by Descartes. And the third one is our focus today, squaring a circle. This problem on geometrical construction proved to be an impossible problem when pi was proved to be transcendental by Lindemann in 1882. So it's a historical problem. So now I'll start with a ready-made some slides which I got from the courtesy of Witold Ignacy Wieslaw from Poland. He's a mathematician and historian of mathematics. So I'm using slides. So courtesy to him. So I'm using his slides, please. Let me see. So the problem is very simple. So we have a circle of unit radius, and the problem is to convert this circle with the area. We know that area is twice pi r, pi r square. It is pi r square, r is equal to 1. So it is just area is equal to 1. The problem is to construct with the help from this simple circle of unit area into a simple rectangle like this, square. And if you want to have the area equal to pi, then the side of this square should be root pi. Now the problem is whether we can convert such a circle into a rectangle by using our, at that time, available resources, that is ruler and pencil or pen, whatever it is. So this is a very simple problem. It looks very simple, but we know that now this simple problem has given thoughts to many new mathematical destinations or directions. I think the circle is traditionally called Quadratura Circulia in Latin, because at the time, most of the language they used was Latin language. The problem is equivalent to the rectification of a circle. So I have electricity, but I'll be using the same system. The problem is equivalent to the rectification of the circle. That means circle converting into a square. That is to the problem of constructing in the same way by ruler and compass a segment of the length equal to perimeter of the circle. And perimeter of the circle is twice pi r is equal to 1, so it will be twice pi. The problem leads to the construction of a segment of length equal to root pi. can we construct with the help of ruler and compass a length of root pi? So this is the problem. Simple problem. So the history of the problem is long because we are talking about 16th century, starting from 16th century. So we'll discuss some example of the efforts in the direction from the period within 16th to 18th century. Let's start with the work of an Italian mathematician. He is also engineer, also a surveyor at the time, and also a bookkeeper, because at the time they were doing multifunction. A person was doing multifunction. So because the whole world was with limited people, population was very low. So everybody had to do a lot of work. It's from the Republic of Venice, from Italy, called Niccolo Fontana Tartaglia. He is from 1500 to 1557, so from 16th century. So this is a drawing of this mathematician, engineer, whatever it is, Niccolo Fontana Tartaglia. So he did only for 57 years. Here I have put, here is the title page of part 1 of General Trattato di Numeri, that is General Treatise on Numeral, Number and Measures, published in 1956 by this Niccolo Tartaglia. This is an extension work on elementary mathematics that was popular in Italy for several decades after its publication in 1556. So in my library, I have a lot of such front page of this old books. And here you can see, it's in Roman. This Roman letter is MDLVI, which is equivalent to 1556. So those who know Roman numericals, they will understand this is 1556. Anyway, now let's look at a bit biography of Niccolo Tartaglia. So he was, Tartaglia presents in the above book, which I have mentioned here, shown here, the following approximate squaring the circle. So that means we have to first find how much is root pi. He transforms a square into the circle. He does the reverse one. He transforms a square into circle, dividing its diagonal into 10 equal parts and taking as a diameter of the circle 8 parts. I'll show the picture here. So this is the drawing from his book. So what he did is he did the reverse one. He took a square, and from there he drew a circle, and he tried to convince that the perimeter of the circle is equivalent to the perimeter of the square. A simple calculation shows that the construction leads to a Babylonian approximation of pi. So Babylon has given the approximation of pi equal to 25 by 8. Generally, we say 7 by 3 or something like that. Anyway, so Babylon has given the approximate pi as 25 by 8, and his constructions show that it is very close to 20, for the value of pi will be 25 by 8. Here we have another book in the 16th century. Here is the title page of the General di Quadratura Circuli. You can see they are all Latin names. The Quadrature of the Circle, published in 1559 by Jonas Buttionians. He is a French mathematician. This is the title page of this book by Buttionians, the Quadrature. So John de Buttionians, sometimes known as Johannes Buttionius, refuted the pretension of those who claim to have found the solution of the quadrature. He said it's not very equal, not very easy. Those who have said that we have found it is not totally correct. He presented construction leading to Ptolemy's approximation of pi. So pi is 327 by 120. You can see now the value of pi is being improved. Once the value of pi is improved, you can find the value of root pi, and of course you can then construct a square equivalent to the area of a circle. And a third book here I have put here is the title page of third book. It is the page of the appendix Encyclopedia in an quadrature circuli, that means making a circle from a quadrature or square from a circle, is appendix chromateria SNSVA, which affirms the square circle. And it was published in 1594 by Joseph Scalier. He is also a French mathematician. In this way, after every few years, then the approximate value of pi was increasing, being more correct, and then we will be able to construct a square equivalent to a circle in a more and more correct way. Who is this Joseph Scaliger? Joseph Scaliger takes root 10 for pi. Root 10 is 3 point something in his construction. He draws diameter d equal to twice r in a circle. Next, the middle point of its radius, and construct rectangular triangle with legs 3 by 2 r and half r. This hypotenuse gives, in his opinion, an approximate squaring of the circle, that is root pi. And there's another book. Here is the title page of the Verinium, the Robust Mathematician Responsorium Libri 8. That is a various replies book about mathematics 8, published in 1593 by Francis Vete. It's again a French mathematician. So you can see it started from Italy, but more and more work were done by French mathematician. So his construction, Francis Vete's construction, is well known as the author of literal notations consequently used in the algebra. So before that, it was done something like a manual one, but he has now used this notation. And this notation leads to what is known as algebra in the later phase. So it represents some approximate construction of squaring and equification of the circle. On page 26 of that book, I have put a part of that page 26. Here you can see the circle over here, and you will find the radius over here. So what he does is, on page 26, we can find the following exercise. Quadrant circumferentia data circum invenia proximally, he writes that in Latin. Find the segment approximately equal to the quarter of the circle. So he finds the quarter of the circle, and from there you can make a complete circle. The figure on the page in the previous one, I have drawn on my own. It looks like this one. So let me explain this figure. In this figure, AB and AD being the radius, they are equal, of course, equal to A, the radius. DF and FA, so is the middle point, F is the middle point, and EI and BZ over here. So you make the chord of Z over here equivalent to this one. Here he draws a parallel line over here. So EK is parallel to IS. VT claims that EK, this EK, the bigger one, the EK is approximately equal to the quarter of the circle BDCE. So the similarity of the triangles, AIH is a small one, this AIH is a small one, and AEK, this AEK is the bigger one. So this small circle, a small triangle, and big circles, big triangles are similar triangles. If the triangle is similar, then the ratios will be equal. Then he says A1 by 8 AE will be AS by AK, and from here he makes a calculation. So I will not read the calculation, but you will find the value of P will be AS twice 2 times AS by AI. So he makes the ratio of this sides of this triangle. Using simple calculation, it finds that pi will be 3 upon 5, 3 plus root 5, which will be 3.14116, which is very close to the pi, very good approximation of pi. So this is how you can see year by year, the value of pi is being improved. And once the pi will be increased, you can find the value of root pi, and the problem will be solved. And then another mathematician, Kosansky, is approximation of pi. So Adamandi Kosinski was a Polish mathematician. He's also a physicist. He also makes a clockmaker. He's a pedagogue and also a librarian. You can see they are multifunctional people over there. Now we are coming to 17th century. From 16, we are now jumping to the 17th century. And This Konski was the first professor of mathematics in Mainz in Poland in 1659. In his 1685 paper, Observation Cyclometrics, published in Acta Eruditorium, this Adam D. Kochenski presented an approximate ruler and compass construction for rectification of the circle. So this is how he draw. He started with drawing a semicircle. So he didn't draw a whole circle. He drew a semicircle of radius 1, radius being 1, so AC or AD they are being equal to 1, inscribed in a rectangle BGD. So he inscribed, he draws a rectangle over here. Then we draw a line AI over here, AI, such that angle IAC will be 60 degrees. So we make a 60 degree and call the I over here, such that AIC will be 60. When the lower side of the rectangle is extended, here you can see it has been extended. Lower side of it is extended it to H. HL is extended, is equal to the diameter of the circle, and a line is drawn from I to L. One can easily show that IL, dimension of IL, will be 1/3 of root, that all simple arithmetic calculation using equal triangles on the 20 minus 18 root 3, which will give us 3.141533. So you can see the value of pi is being improved in each step. Now we are coming to the 17th century. Then we have Christian Huygens. Among the many authors who kept busy in the 17th century with measuring the circle was Christian Huygens, 1629 to 1695. He learned that extended the coordinate method of Descartes, showing its many applications in mathematics and elsewhere. In the treatise De Circuli Magnituda Inventa, a study of the circle magnitude, from the year 1654, he described different geometrical methods of approximating the perimeter of the circle. So this is the Christian Huygens drawing. So let AOB be a circle with radius r, and angle, let angle alpha यहाँ देखिए ना, let OC bisect the angle AOB. See, we are bisecting this angle alpha and OC, bisect the angle, and you will have the angle AOB bisecting over here. We put CD, we put CD is equal to AC, so we extend this over here, AC to CD equal, in AC is equal to CD, on the line through AC, the circle with centrum A. Now we draw a circle with center A and B in G. So we extend this up to G over here. Finally, put DE, small part, this is small part. This is equal to 1/3 of BG. Small part, this is BG is here. I put D is equal to 1/3. Then as Huygens claims, the length of the arc AB, length of the arc AB is approximately equal to the segment AE. Segment AE. So this curve is equal to, in length, the straight line AE. So this is his method of converting a curve into equivalent straight line. Another mathematician is Isaac Bruckner. Isaac Bruckner, again 17th century. Actually, he did the work in 18th century, 1720, and he constructed his first globe in Basel and developed a swindling globe until 1725. Bruckner received a call to the Russian Academy of Sciences in St. Petersburg from Leonhard Euler in 1733. About Leonhard Euler, we'll talk after 2-3 seminars. We'll have a life and work of Leonhard Euler, the greatest mathematician in the world. There he taught mechanics and produced mechanics, devices, tools, and cars. He went to St. Petersburg in Russia. In 1754 and 1755, he and his colleague Daniel Bernoulli, so Daniel Bernoulli is also from Basel, he created a world map and a globe made of gold-plated copper. So a bit of Leonhard Euler, because he's also from Basel. The problem of squaring the circle appears in 7 Leonhard Euler's from 1700 to 1783. He worked very hard, about which I'll give a life history later on. And 1707 to 1783 papers, and in his corresponding with Christian Goldbach. So we'll also talk about Goldbach in the later phase. Goldbach was from 1690 to 1764. So in this year, from 1729 to 1780, within a year, so Euler gave 7 papers. He described one of Euler's approximate rectification of a circle. Euler proposed the following modification of Bruckner's construction. So he improved it. He improved it and found the value of pi very more closer, 3.14149. I'm not going to read all these things. So later on, you will get a PDF version of my seminar, and you can thoroughly, those who are interested can thoroughly look at this simple mathematical arithmetical calculation. Now, this problem, though they have so many mathematicians from 1670 try to improve the value of pi, until you have the correct value of pi, you will not be able to convert a circle into a rectangle, because the diameter should be, the side should be root pi. And so to become correct, we have to find the correct value of pi. But unfortunately, it became, when pi was declared transcendental, then people were convinced that it is impossible to convert a circle into an exact value of a square, the same value. This value is transcendental was given by Linderman, Ferdinand von Linderman, 1852 to 1939, was one of the founder of the modern German education system. So he was a German. He emphasized the development of the seminar, and his lectures communicated the latest research result. So you can say from 19th century, this culture of seminar became very popular. So I am also using that popular seminar system in my connections with this School of Education of Kathmandu University. He also supervised more than 60 doctoral students, including David Hilbert. We'll talk about David Hilbert in the seminar 3, I think so. Anyway, so this seminar is so important. Linderman's main work was on geometry and analysis. He is famed for his proof that pi is transcendental. That is, pi is not the root of any algebraic equation with rational. About this transcendental, this algebraic equation will come later on. In 1973, the year in which Linderman was awarded his doctorate, in 1863, he got the doctorate, and Charles Hermet, another mathematician, published his proof that E is transcendental. Not only pi is transcendental, E is also transcendental, was proved by Charles Hermet. About this transcendental, we'll come again and again back in the series of my seminars. Shortly after this, Linderman visited Hermet, the same Hermet, who told that E is transcendental. So they met in Paris and discussed the method which they have used in this proof. Using methods similar to those of Hermet, Linderman established in 1882 that pi was also transcendental. It does not satisfy any algebraic equation. That means this pi is transcendental, and transcendental numbers don't satisfy any algebraic equation with rational coefficients. So in fact, this proof is based on the proof that E is transcendental. So first, E was proved to be transcendental, and by Hermet, and with the help of Hermet, and with discussing with Hermet, Linderman could prove that pi is also transcendental. And pi was supposed to be was proved by transcendental using the fact that e to the pi I is equal to -1. So about this e to the pi I equal -1, we'll have one whole seminar, S1, after 1 week. Linderman's proof that pi is transcendental finally established that squaring the circle with ruler and compass is insoluble. So it was after 3-4 decades, starting from 16th century, only in 18th century, 19th century, it was finally proved that the squaring the circle with ruler and compass is insoluble. He published this proof in the paper Uber D. Ham pi, that is concerning the number pi, in 1882. His grave, the grave of linear man, has a circle superimposed upon a square surrounding this symbol pi. So in his grave, you will find his grave like this one. You can see this is a grave. Over here, linear man's tomb. Over here, there is a pi written over here. This circle is here, but it is not very nicely visible here. Anyway, so there's another bigger figure over here, which is not very clear in my picture. So this is a memorial of linear man in Munich, in Germany, that has the pi in it. So you can see pi has been inscribed over here. Those who are interested, so I have put in here the link to the slides I have shown over here. That slides I have not made over. It was I have borrowed from the Polish mathematician. Okay, so there are a lot of interesting videos related with this squaring the circle. There's also a very nice math magic, I call it. You can look at the YouTube in this link. So when I send this PDF file, you can watch these videos. Now, related with this prelude, I will say, squaring circle, I will now try to tell about some of the straight edge and compass construction, the historical emerge of these problems. It's a school children's problem, actually. It is a method for drawing a perfect length and shapes with an infinite unruled straight edge. Compass, which can draw a perfect circle of any radius. If you look at the instrument box, there is a compass in the instrument box, if the students know that. For example, construction of an equilateral triangle. So how do we draw a equilateral triangle with the help of a ruler and a compass? So if you want to draw a equilateral triangle with the help of straight line, ruler and a compass, first of all, take 2 points, join it, and taking this as the radius, draw 2 circles like this one. So once you draw 2 circles, the 2 circles will intersect over here, and then you mark this point of intersection and draw the straight line. This is a equilateral triangle which can be easily drawn with the help of a compass and a ruler. Very simple exercise which we teach in the school. So here is the equilateral triangle. The ancients are very wise people. The ancient Greeks were very skilled with compass construction. Euclid detailed a great many, including division of line segment into equal parts, bisections of angles, but they couldn't bisect an angle into 3 parts, construct of parallel and perpendicular lines, construct of regular 3, 4, 5, and 15 cones, and 15-sided polygons. But very little progress was made after Euclid. So Euclid started with it. You can see it started with Greek mathematician Euclid, but after that, no serious attention were given to this very seemingly simple problem. In particular, no new polygon constructions were found except 3, 4, 5, and 15. No other polygons with many-sided were found until this concept of polygon is again another history. The Greek mathematician knew that a regular n polygon is constructible if n is an integer of the form n is equal to 2 to the power k, 3 to the power r, 5 to the power r, where k is a non-negative integer, which is r, which is this r is value is equal to 0 and 1. K is non-negative integer, and r can take value only 0 and 1. So if this n is equal to value given with this value of k, r is equal to 0 or 1, then we'll be able to find a regular polygon with the help of ruler and compass. So let me make a table what type of polygons you can make. This lesson does not describe all the constructible n polygons, but the following n goals were familiar to the Greeks. So n is equal to 3. So put the value of k is equal to 0, r is equal to 1, r is equal to again 0. You can put the value of r is equal to 1 or 0. Then you can make a triangle 3. You can make a square, because this value will give us, this value will give us 0, 0, 2 square is 4. This value will give us 1, 1, and 5 will give us 1. So this value is giving us 6 and 6 only. So you can make a hexagon, you can make a octagon, you can make a decagon, so you can make a pentagon. So with the help of this Greek formula, 2k, 3r, 5 pi, where k is 0, 1, and so on, and r can be only 1 and 0. With this combination, it was found that you can make a triangle, you can make a square, you can make a pentagon, you can make a hexagon, you can make a octagon, you can make a decagon, you can make a 15-sided polygon. Then what about the other type of polygons is the question now. Now, one of the very strange type of mathematics is called Friedrich Gauss, a 18th century mathematician, 18th century mathematician. On June 1, 1796, the following column was posted in a journal called Geometrical Intelligentsia, Intelligent Math. So he wrote that in this journal on June 1, 1796, anybody starting to learn geometry understand that geometrically various regular polygons like triangle, pentagon, 15-sided polygon, and those polygons which are obtained by doubling the side of these can be constructed. Once you can construct 5, you can construct 10. Of course, you get only half, do it half, and you'll get 10. So this was known from the day of Euclid. However, one has added nothing to these discoveries, and I am astonished that one could not achieve any others by geometrical construction. So he didn't put any problem, but he was amazed that people were not working on this line of drawing different-sided polygons, except these few ones. And in this June 1, 1796, General Intelligence, he writes that, even then, I like to draw attention to the fact that besides above mentioned polygon, several other regular polygons are possible to construct geometrical, including the heptadecagon. Heptadecagon is 17-sided polygon. So,
You have a call. Please pick up the phone. Gopal Bahadur You have a call. Please pick up the
म अहिले एउटा सेमिनारमा छु, पछि फोन गर्छु म. Okay, so the sign of this column was K.F. Gauss, student. He was student mathematician in Göttingen. Even at the age of 19, you can say at the age of 19, he put this problem over here. He said that it is possible to construct geometrically, including the heptadecagon 17-sided. Up to 15 it was okay. Now 17-sided, nobody has tried, and he said it's possible. Gauss has found on March 30, 1796, that it was possible to geometrically construct a 17-sided polygon. In fact, he has found that the necessary and sufficient condition for the construction of regular polygon are that the number of sides must be a prime of this form. If the number of sides has this 2 to the power n 1 value, then you will be able to construct a polygon with the help of a ruler and a scale. Compass. The compass, where n is a non-negative integer. Such primes are called Fermat primes. About primes, we'll talk about later on also in our number theory. It shows that following n goals are some more constructible. 15 some the भनिसकेको 3, of course, we can do that. 5 pentagon. So heptagon is possible. Even this 257 gon and 65,537 gon are also possible. That is what Carl Friedrich Gauss showed. Now, in the following slides, I'll try to show you how heptadecagon is constructed according to him. This coming slides, is based on the presentation I have made at ICMA 12. ICMA is International Conference on Teaching Mathematical Applications on 12. It's ICMA 12, London 20, UK. It was in City University in UK. The conference was held from August 1 to 9, 2018. Just like to those some of you may be knowing, ICMA 13 was held at Kathmandu University. Okay. यो होइन यो 2018 होइन यो 2005 हुनुपर्ने हो गर्नुभएछ त्यहाँ यहाँ डेट गर्नुभएछ anyway I was there in 2007 it was ICMA 13 was held in Kathmandu so I was there 2005 हो यहाँ डेट गर्नुभएछ मैले कहाँको साइड राखेर so it was held from 10 to 14 July 2005 at City University London. You can see me there making presentation of the construction of the Pentagon. So we also had a very tour of Thames River over there in London. This is Queen's Mary's ante room where we had our dinner, one lunch, one dinner there. And we also, of course, once we are in London, you should visit Buckingham Palace. So I was with my wife and my first PhD, Dalbar Adhikari, was in UK at the time, working over there. So he invited me for a small gathering over here at his residence there. Of course, he has come back now. Now, when we visit some of the nice places over here. This is a plaque for Peter Neyman, anyway. And we visited what is called Greenwich timeline. So here on left and right, you will have two different times, AM, PM or something, whatever it is. It's in Greenwich. Okay. And we also had a tour. Now, let's come back to construct with a compass and ruler. So this is the slides I have presented there in ICMA 12. The basic things we can construct with a compass and ruler are lines, circles, and a combination of these. For a given line of unit length, it is possible to construct lines of only those lengths which are obtained by the finite times application of the four basic arithmetic operations, that is addition, subtraction, multiplication, and division, and taking the square roots. Such a value obtained is called a quadratic irrational. Only a length of quadratic irrational is possible to construct with a compass and a ruler. So if you know that this length is quadratic irrational, then you can construct such a length with the help of compass and ruler. The problem of construction of n-gon is equivalent to dividing a circle of unit radius to n equal parts. In this case, the length of the chord, which forms the side of the n-gon, is equal to 2 sine pi by n. Okay, we divide the circumference into n. For all n, when this is a quadratic irrational, n-gon is possible. So if you can find that this value is quadratic irrational, if you can prove that this value is a certain value of n, then you will be able to construct the polygon by using a ruler and a compass. It is obvious for n is equal to 3, 4, 5, and 6. That means a triangle, square, pentagon, and hexagon can be constructed. We now show that it is quadratic irrational for n is equal to 10 also. So we have to show that 2 times sine pi by 10 is quadratic irrational. Construct an equilateral triangle ABC with side AB is equal to BC. And B is equal to pi by 5. If you construct like this, if you take AB is equal to 1 and BC is equal to 5, this is an equilateral triangle. So these two sides are equal, 1 and 1. Then the angle B, you can calculate, will be pi by 5. So draw the angle bisector AD. So I'll draw the bisector AD. Then X will be equal to, of course, it is AC. Also, it will be equal to AD. Also, it will be equal to BD because this is the bisector. And that will be equal to 2 sine pi by 10. So we have BD. So it's a question from similar triangles. BD by DC will be AB, bigger side, by side AC. And so if you put the value of x, it will be like this one, x by 1 minus 1, and 1 by x, which will be give rise to the quadratic equation x squared plus x minus 1 equal to 0, and the root is equal to x root 5 minus 1 by 2, which is an easy way of finding the quadratic equation. And so this is already a quadratic irrational value, so it's very easy to find the value of pi by 10. And that's so that 2 sine pi by 10 is quadratic irrational. Now, to find n-gons, we have to find the roots of unity and n-gons. Gauss used the imaginary number to solve his real problems. So Gauss was very interesting mathematician. So he used imaginary number to solve the real problem. Real problem is to construct the n-gons. The terminal points of the roots of unity, which are the solutions of the equation z to the power n is equal to 1, are the vertices of n-gons. So for the different values of n, we have to find the solution for this z to the power n is equal to 1. We can show that these roots are quadratic irrational. Then if you can show that these roots are quadratic irrational, then the n-gon is constructible. So the problem is now leads to finding the solution of the quadratic equation z to the power is equal to 1 for different values of n. This equation z to the power n is equal to 1, we can reduce mathematically in this way. I will take jn minus 1 here, jn minus 1 equal to 0. So then I can take z minus 1 out, common, then the value left will be zn minus 1 plus zn minus 2 plus n up to 1 equal to 0. And so one of the solution is, of course, easily z equal to 1. The roots are z equal to 1, and the roots of this remaining quadratic n minus 1 root over here. These roots are, then you can find the roots will be something like this. You can use the trigonometric function over here. The roots will be e to the power, ek will be cos twice by kn plus 1 plus, because there is a method to find the roots of this one, and 1 k from up to 1 only n plus 1. We are up to only 1 to 1 plus 1. For n is equal to 3, the roots are minus 1 minus I root 3 2 and minus 1 minus 1. It's a plus minus, you will get plus minus here over here. n is equal to 1 to पहिला आइसक्यो 1, z is equal to 1 to छ नै छ. So these are another two roots. Both of these are quadratic irrational. So then that means for n is equal to 3, that means triangle we can make. For n is equal to 5, we look at the 4 roots. The one root is z is equal to 1 is already there. We are talking only of the remaining 4. So we look at the 4 roots of this equation, z to the power of 4 plus z to the power of 3 plus z squared plus z plus 1 is equal to 0. The roots will be epsilon 1, epsilon 2, epsilon 3, and epsilon 4. 1 is already there, 1. The roots can be written as, so this equation you can write z squared plus 1 by z squared plus z plus 1 by z plus 1 by z. So you can see the way they use the mathematics. And you can see then you can write as z plus 1 whole square plus z plus 1 minus 1, reframing over here. Now if I put z plus 1 by z is equal to denote at w, then it will again convert into a quadratic square. Quadratic equation. W square plus w minus 1. So it's the same equation as we have here. And this will, of course, give a quadratic value, quadratic irrational value. So the roots of this equation are w 1 to 1 plus root 5 by 2. So w is equal to here. We put the value of w over here, and then you will find the value of z. So z plus 1 by z w1, and z plus 1 by z is w2. The roots will be like this, ek, and it will be like this one. You can see the roots will be located in this 5 way. Then you can see now you have been able to construct a pentagon. Okay. The first one is z is equal to 1 is already here. The other roots are scattered 1, 2, 3, 4 are scattered over here. E1, E2, E3. E0 has value 1. Z is equal to 1. So in this way, pentagon is possible. First real number of roots Ui is equal to, so you can, it is just to show that these are all quadratic irrational numbers. And once we know that it is quadratic irrational, then we'll be able to construct with the help of, this shows that the pentagon is constructible. So how do we draw the pentagon physically? That was mathematically, we have shown that it is possible. To draw a pentagon, draw a circle with center at O, two mutually perpendicular diameters, of course, AB and AC, divide E. Divide by E, the radius AO, divide over here into half. So we'll put a mark over here. And join EC with E as center, EC as radius, EC as the radius. Draw an arc to intercept the radius OB. Okay, intercept radius at OB at EF. So EF. So up to here. Then after that, with C as the center and CF as the radius, draw an arc to intercept AG. CF as radius, draw an arc to intercept the circle at G. I'll draw it. Oh, it will intercept at G. CG, this CG is one of side of pentagon. Oh, okay. And with G as center of CG as radius, once you find the one side, then you can mark and mark and mark, and the pentagon is constructed in this way. Now, the problem of heptadecagon. So now put the value of n is equal to 10. Gauss was interested with two basic problems: periodicity of the digits when one is divided by the prime numbers. This led to the problem of finding such k which will divide 10 to the power k minus 1, and the theorem p is, if a prime, t to the prime minus p is always divisible by p. For what values of a, the quantity a to the power k minus 1 is not divisible by p for p or k less than p minus 1. Such a prime p is called a primitive root of a. The existence of the construction of a regular heptagon was first demonstrated by Carl Friedrich Gauss again on 13 March 1796 at the age of 19. So I have already given this fact earlier also. So he did it at the age of 19. Existence of construction of a regular pentagon was first demonstrated by Carl on 13 March 1796 at the age of 19. Some sources suggest that it was his discovery that led to consider mathematics as a career option. So once he could construct a regular heptagon, then he has interest in mathematics, and he became a Carl Gauss. Friedrich Gauss became a great mathematician. The construction given here in the following slides is the one given by Herbert William Richmond in 1893. Though Gauss gave the demonstrative method in 1796, but the real nice method is given by later on by Herbert William Richmond in 1893. Okay. And this method by Herbert William Richmond is, I found it from this concept of regular heptagon, from this link, in the Google. Gauss found that 4 is equal to 3, the primitive root p is equal to 17. This means when you divide 3 to the power k by 17, the remainders are 1, 2, 3, up to 16. You can see over here the 4 different values of a. 3 to the power k will be over here, 1 to 3, 2 power 9, 3 to the power 27, 81, and so it goes on. And if you divide these numbers by 17, for example, if you divide this by 17 by 17, the remainder will be 13. If you divide 81 by 17, the remainder will be 3, 13, and so on. So remainders are here, the values of 3 to the power over here. So this is the table found out by, calculated by Gauss. Gauss used this result to group up the roots of the equation. So since we are trying to construct heptadecagon, that means 17-sided, so we have to solve this 16th power equation, z16 plus z15 up to z plus 1 is equal to 0. Gauss assigned new index to the roots. So instead of epsilon k, which is the root of this equation. So he used the previous table. The roots with a new index L, so that is new, corresponds to like this. If it is the for EK, root EK, you will make the new assigns like this. It will denoted by EL, the new one. Is a root with the new formation. That is rearranging the roots. If K is the remainder, then L is divided by 17. So K is identified from the third row of the table, corresponding to the L in the first row. With this system of index routing, rerouting, that means Gauss grouped these roots as a chain of nested quadratic equation. So one quadratic equation there, it will give a quadratic irrational value. So he put a quadratic equation into quadratic equation into quadratic equation like this one. Up to 16. Yeah, we have to find the problem up to j to the power 16. So, and he also notes that the product of EK into epsilon K roots will be equal to found as the root epsilon of K plus L. If K plus L is equal to 17, then K plus L is replaced by the remainder after dividing by 17. And EK root will be written as E1 to the power. Then you can write as E1 to the power K. So instead of this root, sum of these roots, 16 roots, it makes the sum of this new index roots, and we will find that the value is equal to -1. And if you denote the sum of 2, so denote by root gamma, sigma m gamma, the sum of these two for such K primes gives the remainder R divided by R. Then we have the first group EK. So if you want to use this, you have to use first called UK. So we go on finding the sum of even one, odd one, and so on. So this is all arithmetic he is doing like this, making different type of, and then he makes a sum of these two obtained over here, and also product of these two. So in this way, he goes on playing with these roots to find the real numbers required for the construct of heptadecahedron. The quadratic, that means he has to show that the roots obtained, whatever in way he is doing, will be quadratic irrational. So that's how he is playing with these numbers. So then he will find that these roots will be, again, you can see, again it's a quadratic equation. But here the coefficient is -4, not 1. In the previous we had -1, here we have 4. Those of the equations are very similar over here, but it will be again quadratic irrational. It will be again quadratically irrational. So he goes back, and he finds all these roots over here, which I am quickly showing here. So not very interesting to many, may not be very interesting to all of you. So since I will be sending the PDF, you can minutely look at these values. So in any way, he comes back to the quadratic equation. But only the difference is here you will have 4, not 1, as in the previous quadratic equations. And main object of Gauss is to show that these values finally will lead to quadratic irrational values. So I am quickly going here. It is not interesting to read all these mathematical symbols. I have meticulously worked again. See, whatever you do, it will always convert into quadratic equation over here. And so instead of sine, we have here cos over here. This is a quadratic equation. So finally, he shows that it will be a quadratic equation. You can see finally he shows that it is a quadratic equation. So this shows that a heptadecagon, a 17 polygon, is constructed with a compass and rule. Finally, he shows that the root of this j to the power 16 plus j to the power 15 and so on plus 1 equal to 0. The roots are all quadratic irrational. Once the roots are quadratic irrational, this will show that a heptadecagon is constructible with the help of compass and ruler. And now, theoretically, it is possible. Now, how to really construct the heptadecagon itself? The elegant method for construction of heptadecagon was given by Richmond, I have told earlier also, in 1893. Given an arbitrary point O, draw a circle center at 0 and radius OP. O. So radius is here, and we take a radius P0. OP0 is the radius. Okay, first point. Construct the radius OB perpendicular to OP. And so, of course, you can easily draw the perpendicular with the help of compass and ruler. So we have B here. Construct J a quarter of the way up to OP. So we'll divide it into 4 quarters and then mark it over here. J. Join JPO. Draw a line here. So we'll have a triangle over here with OJE, OJP0. Join JPO and find E. Now I have to find E so that AJE, which I have to draw, is quarter of OP, OJP. So from here, I'll find a quarter of it and then draw the triangle OJE. Let me draw the triangle AJ where it will go. Oh, over here. So this small angle is quarter of this big angle. So I have point E also. Find F so that EJF will be 45. So here from EJ, I have to draw an angle of 45. Let me draw an angle of 45. So from here, add something here so that the angle will be 45, and then I'll get the point F. Construct the circle with radius FPO. So this will be then the new radius for this circle, new circle. Construct a circle with radius FP0 to cut OB, this radius OB at K. So I take this as radius and cut it here. Let me see where it will go. Oh, here it is. It has come over here, K. K. Draw a circle with E. Draw a circle with E as EK as radius to cut OP0. Now I'll have another point N3 here, N3 here, N3 and N5. So once you draw circle over, I have 2 points N3 and N5. Construct the line perpendicular to OP0 through N3 and N5. From N3 I have drawn, from N5 I have to draw. Okay, N5 I have to draw. Meet the original circle at P3 and P3 I have shown. P5 is here, P5 respectively. Arc P3, P5, this arc I have found is equal to 2/17 of the circle. 2/17. So I have to half it to make it 1/17 of the circle. So that means the middle of P3, P5 gives P4. So let me put the middle of this one, P4. This is P4. P4. So using P3, P4, this is part over here. Get the remaining points of the heptadecagon around the circle. So I am putting all these values equal to over here. P6 I have put here, P7 and P8, P9, 10, 11, 12, that will be 16, 17 up to. Okay, over here. Now, if you join this at segments, P1, P2, P3, P4, P5, P6, P7, and so on, then you'll have the connecting the adjacent point P0, P1 up to P16. Okay, then you'll have the heptadecagon. The required heptadecagon is constructed. So to not make it clumsy, I have not put the segments for. You have to put a straight line. That means segment P1, P2, P2, P2. You have to draw over here. If I draw, it will be not very nice. So you will be able to construct a heptadecagon in this way. So it will be, I have taken the circle. One the heptadecagon is left over here. Now this is 17-sided polygon over here. So P1, P2, P2 up to P17. And over here, you can see one side, two side, another side over here. Okay, so that is how a heptadecagon is constructed. So we call Gauss as the prince of mathematics, because at the age of 19, he could do such a miracle in mathematics. Construction of a 17 heptagon, which was thought to be impossible in the earlier time. Only up to 15 was possible for the 17th century people. But goes, then prove that you can do up to 19. Not only 19, he also showed that you can do for 257 and 6,065 and so on and so on. Okay. Now, since we have a computer system, a lot of things can be done easily by construction, by computer, with the help of computer. And so very nice picture like this. For different values of z, you can see, this is for 0 of 15. You can also make for 0 of 15. You can find the root of z, and then, okay, over here, let me once more show this. Okay, also over here. Now, this is seminar 1. As you know that this is more focused for education people. So for education people, the more interest is they become good teachers. So in my experience and working for a long time, to draw the attention of the students in one course, then what I do is, when I have the first lecture, I tell them a story. Then I say it's a story time. In my whole 15 to 16 lectures or seminars, so I'll have one story at the beginning. There will be one story at the middle of the seminar, somewhere after in the 8th lecture or seminar, and then there will be one story at the last. So I'll be telling 3 stories to motivate the students, which gives some let's say our way of thinking will improve over here. So story time. And generally, since we are all Nepali, I like to tell a story in Nepali. ठीक छ? नेपालीमा story भन्छु म. Okay? So I am a student from Russia. So then I should start a story from Russia. So यो मैले रुसमा पढेकोले म कथा चाहिँ नेपालीमा भन्छु है त, नेपालीमा भन्छु कथा है, नेपालीमा कथा भन्छु. यो चाहिँ नि 3 questions by Leo Tolstoy. Leo Tolstoy is a Russian writer, 1828-1910. ढाई साढे चार लाग्छ एकदम. सो उहाँको यो धेरैले सुनेको होला, फेरि 10चोटि सुनेको पनि के हुँदैन, कथाहरू त सुनाइरहेको हुन्छ, सुनिरहेको हुन्छ. Okay. So there's a 3 questions by Leo Tolstoy. Key question was, how do you tell the right time for every deed, action? How do you know who are the most essential people? How to decide which pursuits are the most important? कुन काम सबभन्दा राम्रो हुन्छ, कुन टाइममा सुरु गर्नुपर्छ, राइट टाइम, who is the most essential people भनेर 3वटा क्वेसन चाहिँ एक राजालाई, एक राजाहरूको काम त्यस्तै हुन्छ. सबै चाहिँ त्यहाँ मन्त्री सन्त्री जम्मा गरेर ल मलाई यो 3टा क्वेसनको एन्सर चाहियो, ल भन्नुहोस् भनेर चाहिँ भने. अनि यो राइट टाइमको त आफ्नो आफ्नो हुन्छ. बिहान चाहिँ यो हाम्रोको चाहिँ घैँटो भरेको देख्यो भने पनि राइट टाइम भन्छ, कहिले केलाई राइट टाइम भन्छ, कहिले यसलाई राइट टाइम भन्यो. अनि वाट मोस्ट एसेन्सियल पिपल भनेको त धेरैले राजा नै मोस्ट एसेन्सियल पर्सन भनिहाल्छ. त्यो यस्ता यस्ता चाहिँ भन्न थाले. के कामसम्म राम्रो हो भने टेबल आउँदा सायद चाहिँ अर्को देश जित्ने नै राम्रो भनेको होला, के भनेको होला. बट ही वाज नट सेटिस्फाइड विथ एनी अफ द एन्सर गिभन बाई हिज कोर्टयार्ड्स. भएपछि अब के गर्ने, आफ्नो क्वेसनको एन्सर आएन भने त्यो राजालाई दिक्क चाहिँ भएको थियो. अनि त्यही दिन 1-2 दिनपछि उसको एकजना सल्लाहकारै भनौँ न, सल्लाहकारले के भने, महाराज यसको क्वेसन एन्सर दिने त एकजना मात्रै छ, एकजना मान्छे हुनसक्छ, त्यो चाहिँ नि यहाँ बस्दैन, जङ्गलमा बस्छ, यदि हेरमिटेज, ऊ चाहिँ नि ऋषिमुनि हो, त्यो ऋषिमुनि मात्रै चाहिँ यस्तो क्वेसनको एन्सर गर्न सक्छ, साँच्चैको एन्सर दिने ऋषिमुनि हो भनेपछि. अनि के गर्ने त भन्दाखेरि ऋषिमुनि कहाँ गएर सोध्नु पर्यो. तर त्यो सल्लाहकारले के भन्छ, महाराज ख्याल गर्नुहोस्, त्यो ऋषिमुनि चाहिँ एकदम साधारण मान्छे हो, साधारण व्यक्ति हो. उसलाई चाहिँ नि यस्तो टरप ढरप राजा आएको, यो आएको, त्यो आएको उसलाई मन पर्दैन, जेन्टलम्यानहरू आएको मन पर्दैन. उसलाई साधारण मान्छेसँग मात्रै ऊ डिल गर्छ. त्यहाँ तपाईँ चाहिँ नि साधारण मान्छे जस्तो गरेर जङ्गलमा गएर यो क्वेसन उहाँसँग सोध्यो भने यसको जवाफ पाउँछ भन्ने चाहिँ नि भयो. त्यही भनेपछि चाहिँ उहाँले हुन्छ भनेर केही समयपछि त्यो ऋषिमुनि कहाँ जाने भनेर दरबारबाट निस्कियो. र चाहिँ छेउमै चाहिँ जङ्गल सुरु हुन अगाडि नै कोडा सोडा आफ्नो सबै लुगाफाटाहरू चाहिँ चेन्ज गरेर साधारण मान्छे, सिम्पल मान्छे जस्तो भ्याङझुङ गरेर एकदम यात्रु जस्तो गरेर जङ्गलमा एक्लै पसे. र जङ्गलभित्र गएपछि एउटा कुटी देखेपछि त्यहाँ ऋषिको दर्शन भयो. अनि दण्डवट गरेँ के गर्नुपर्ने अनि गरिसकेपछि चाहिँ नि अब कहाँबाट आएको भनेर सोचेँ म यसो चाहिँ नि जङ्गलमा यताबाट उता जान खोजेको बाटो हराएको जस्तो लाग्छ यहाँ कुटी देखेर आएको हो म यहाँ केही दिन बस्नु सक्छु केही आराम गर्न सक्छु हो यु आर मोस्ट वेलकम ल बस्नुहोस् भनेर त्यो ऋषिमुनि कहाँ बसेँ है अनि पहिलो दिन गएर आराम गरेर थाकेको आराम जस्तो गरेर बसेँ अनि भोलिपल्ट चाहिँ नि उठ्न साथ चाहिँ ऋषिमुनिले ल यो पानी लिएर आऊ यो ल्याऊ त्यो ल्याऊ भनेर त्यो राजालाई काम अरायो उसले पनि आफ्नो क्वेसनको एन्सर लिनु छ जे चाहिँ नि राजाले चाहिँ नि त्यो ऋषिमुनिले राजालाई भन्यो राजा चाहिँ नि साधारण मान्छे जस्तो सबै काम गरिदिए है पानी ल्याउने फलफुल टिपेर ल्याउनेदेखि लिएर यो लकडी सक्डी ल्याउने सबै गरेर खाना पिए खाना भयो त्यसपछि अलिकति आराम गर्ने टाइममा चाहिँ नि राजाले चाहिँ नि साधारण मान्छे जस्तो भएर मेरो मनमा यस्तो तिनवटा प्रश्न आएको छ हरेक काम सुरु गर्नलाई सबभन्दा राम्रो टाइम कहिले हुन्छ सबभन्दा चाहिँ इम्पोर्टेन्ट पर्सनहरू व्यक्तिहरू कसलाई भन्ने मैले के काम गरेँ भने मेरो सबभन्दा इम्पोर्टेन्ट काम हुन्छ मोस्ट इम्पोर्टेन्ट काम के होला मेरो लागि भनेर चाहिँ नि कुनै व्यक्तिको लागि कसै होला भनेर चाहिँ सोचेपछि ऋषि मुनिले के भन्यो भने यस्तोको जवाफ मैले दिएर आउँदैन कसैले दिएर पनि कसैलाई पनि छिटो बुझ्दैन यसको क्वेसन जवाफ दियो यो चाहिँ नि स्वतः उत्पत्ति भएर आउने समयले नै देखाउँछ यो आफै इभल्भ भएर आउँछ यसको जवाफहरू भनेर भन्यो त्यस कारण तिमीलाई यो क्वेसनको एन्सर चाहिन्छ भने 1-2 दिन चाहिँ नि यही मसँग चाहिँ नि मैले सेवा गरेर बस्यो भनेपछि होस् भनेर बसेँ र दिनदिनै त्यही चरिया चाहिँ अलिकति गर्ने अलिकति तरकारी सरकारी रोप्ने के रोप्ने खेतहरू पनि चाहियो किन खानु पर्यो त्यहाँबाट त के पहिले त्यो टाइममा त किनेर खाने कुरा भएन बजार भएको कुरा पनि भएन त्यहाँ सेल्फ सफिसियन्ट भएर बसेको हो त्यो भनेर चाहिँ भनेपछि हुन्छ भनेर बसेँ अनि एक दिन खेतमा काम गरिरहेको थियो राजा र ऋषि मुनिलाई हेल्प गरेर राजाले पनि खेतमा काम गरिरहेको घोड सवार भएर छिमेकी मुलुकको चाहिँ नि घुर्रो चाहिँ नि घोडा सवारी गरेर आएर चाहिँ त्यहाँ ठ्याक्क रोके अनि सोझे यो देशको राजा हरायो भन्छ कहाँ गयो भन्छ हरायो भन्छ जङ्गल गयो कि कहाँ गयो भन्छ तिमीले देखेको छौ भनेर त्यो बेलामा त कामै राजाहरू के छ भने एक देशले अर्को देशलाई हमला गर्ने झगडा गर्ने त्यसलाई क्याप्चर गर्ने आफ्नो राज्य ठुलो पार्ने त्यस कारण छिमेकी मुलुकका एक देशका राजा अर्को देशको शत्रु भइहाल्ने त्यस कारण त्यो अर्को देशको चाहिँ नि छिमेकी देशले चाहिँ नि त्यसलाई मार्ने भने मनसायले आएको तर दरबारतिर जाँदाखेरि राजा नै छैन दरबारमा मार्ने मान्छे नै छैन कसले मार्ने हो अनि यताउता सर होइन जङ्गलतिर क्या गरेको जस्तो लाग्छ हामीले भनेर यताउता कुरा गरेपछि जङ्गलमा चाहिँ नि कहीँ होला शिकार गर्न होला के गरेर हेरेको त्यहाँ पनि भेटिरहेको थियो त्यो ऋषि मुनि र एकजना साधारण काम गरेको देखेको छ अनि ऋषि मुनिले के भन्छ भने र दुईजनाले राजाले टाउको मात्रै हल्लायो ऋषि मुनिले यस्तो मान्छे त हामीले राजा सर आएको त हामीले देखेको छैन त यहाँ कन्टिन्यू भइसक्यो हामी यहाँ बसेर काम गरिरहेको छौँ आफ्नै चाहिँ ध्यान गरिरहेछौँ काम गरिरहेछौँ आफ्नै जीविका चलाइरहेछौँ यस्तो देखेको छैन भनेपछि अनि गयो अनि गएपछि ऋषि मुनिले भन्यो ल हेर तपाईँको प्रश्नको उत्तर अहिले आयो अब तपाईँ जुन रूपमा आए पनि मलाई थाहा छ तपाईँ यो देशको राजा हो र तपाईँको धेरै शत्रु पनि छन् तपाईँले मार्नु भनेर आएको हो तर अहिले यो समयमा तपाईँको ज्यान बच्यो किनभने यो समयमा ज्यान बचेको कारण के भन्दाखेरि दिस इज राइट टाइम फर यु यो टाइम तपाईँको ज्यान बचेको दिस इज राइट टाइम फर यु तपाईँको ज्यान बच्ने थिएन दरबारमा बसेर आएको भए यो टाइममा तपाईँ दरबारमा बसेर तपाईँको चाहिँ काल आइसकेको हुन्थ्यो अनि सबभन्दा राम्रो सबभन्दा इम्पोर्टेन्ट पर्सन के भने म हो मैले गरेर तपाईँको ज्यान गयो बच्यो त्यस कारण यो टाइमको लागि यो समयमा म चाहिँ नि तपाईँको लागि सबभन्दा इम्पोर्टेन्ट पर्सन म हो अनि के काम चाहिँ नि भन यो तपाईँले खेत खनिरहेको यो मोस्ट इम्पोर्टेन्ट टाइम हो यो टाइममा तपाईँले खेत खनिरहेकोले तपाईँ राजा होइन साधारण मान्छे भनेर उसले ठानेर गएको त्यस कारण चाहिँ नि हरेक टाइममा चाहिँ नि गरेको काम र पर्सन र यो काम भनेको त्यो टाइमले डिक्टेट गर्छ भनेर म यो कथा भन्छु र कथाको सारांश के हुन्छ भने विद्यार्थीले म भन्छु हेर यो टाइममा सबभन्दा राम्रो टाइम के भन्दाखेरि यो सेमिनार लिने दिस इज द मोस्ट इम्पोर्टेन्ट टाइम फर यु एट दिस टाइम अनि सबभन्दा इम्पोर्टेन्ट इसेन्सियल पर्सन को भन्दाखेरि आई एम द टिचर I am the professor. I am the most important person for you. तर मेरो लागि पनि विद्यार्थीहरू पनि इट्स द मोस्ट इम्पोर्टेन्ट टाइम. अहिलेको लागि, आजको लागि, यो समयको लागि भेरी इम्पोर्टेन्ट टाइम. हु have joined and listened my seminar. These are the most important people for me. अनि के काम भन्दाखेरि the seminar one which I am taking today, अर्को हप्ता that will be seminar 2 will be the most important काम होइन. त्यस कारण चाहिँ नि यस्तो चाहिँ नि हरेक समयले नै समयलाई डिक्टेट गर्छ, पर्सनलाई डिक्टेट गर्छ र कामलाई डिक्टेट गर्छ भने लियो टलस्टॉयको त्यो 3 क्वेशन्स भनेको कथामा चाहिँ नि हरेक चाहिँ नि मेरो क्लासमा सेमिनारको सुरुवातको पहिलो चाहिँ नि मैले गर्ने गरेको छु ल. अब स्टार्ट बढ्दै छ. अब मैले भने यो पुरा मेरो सेमिनार सिरिज चाहिँ नि यो म्याथमेटिक्स थ्रू द एजेस भनेको छ. यसमा चाहिँ नि म्याथमेटिक्स थ्रू द एजेस यसबाट चाहिँ नि डिक्टेट गर्छ. सो इट विल बी यो मैले चाहिँ नि चेकमा भएको सेमिनार भएको समर स्कुल भएको थियो अन हिस्ट्री अफ म्याथमेटिक्स. त्यसको चाहिँ मैले यहाँ सबै चाहिँ नि थुप्रै चाहिँ मेटेरियल लिएको छु. त्यो बाहेक अफकोर्स मेरो कोठामा कति किताब छ भनेको त नेक्स्ट टाइम तपाईँले देख्नुहुन्छ नेक्स्ट सेमिनारमा. त्यस कारण चाहिँ नि यताबाट चाहिँ मेरो सेमिनार चाहिँ नि गइरहेको हुन्छ. सो now we are coming to a conclusion after the lecture. So next seminar will be on September 17, 2021. Okay? And I'll call it yes to second seminar. So the series of this seminar is mathematics through the ages, history of mathematics. So मेरो चाहिँ नि थीम चाहिँ नि mathematics through the ages किन यो 3वटा 4वटा किताब म युज गरिरहेको छु. Of course I have lot of books related with the mathematics. किन तपाईले देखिराख्नुहुन्छ त्यत्रो चाहिँ नि 17औं 16औं 17औं 18औं शताब्दीको चाहिँ किताबहरुको मैले फ्रन्ट पेज र कहीं भित्रको पेज पनि मैले स्क्यान गरेर तपाईलाई देखाइरहेको छु र पछिल्लो आउने सेमिनारहरुमा पनि त्यो तपाईले देख्नुहुन्छ. And the next time on September 17, 2021, the seminar 2 will be on the topic the most beautiful mathematical formula ever. Kati interesting होला त. So next time I'll talk about the most beautiful mathematical formula ever. ल आजलाई यति भयो. ल thank you.
Okay. सक्यो भद्रमान सर?
सक्यो.
Okay. So I think हामी अब एन्ड गर्छौं होला. थ्यांक यू सो मच भद्रमान सर. सो सर चाहिँ हाम्रो लागि एकदमै अब इन्स्पिरेसन पनि एन्ड देन अलिकति रिसोर्स पनि हैन केही अब म्याथ्समा केही गर्नको लागि भोलि अलिकति पर्टिकुलरली हाम्रो यो प्योर म्याथको हैन पोर्सनमा चाहिँ अनि सिमिलरली यो टिचिङ लर्निङको पार्टमा पनि अझै केही राम्रो गर्न सकिन्छ कि भन्ने त्यो पार्टमा चाहिँ सो एकदमै इफेक्टिभ र युजफुल लागिराछ मलाई पनि. So thank you so much, Bhadra sir. This has been, a very insightful session for every one of us. I think participants are really enjoy garnu bhayo hola. So
100+ स्लाइड्सहरु हुन्छ तर म पीडीएफ बनाएर चाहिँ नि त्यहाँ चाहिँ नि नेचरहरुलाई पठाइरहेको हुन्छु. विनोद नेचर कहाँ पठाएको हुन्छु. So anybody who likes to get the copy of the PDF format अब म 5 मिनेटमै पठाउँछु त्यो. यो म एन्ड गर्न आसा त्यहाँ पठाउँछु. You can look at it carefully. जसलाई इन्ट्रेस्ट छ म्याथमेटिकल चीजहरु हेरे पनि भन्छ. अरूलाई चाहिँ नि हिस्ट्रीको मात्रै चाहिँ हेर्ने भने त्यहाँ पनि तपाईलाई जे इन्ट्रेस्ट छ त्यहाँबाट तपाईले ग्र्याब इट फ्रम देयर व्हाट इज देयर इन द पीडीएफ फर्मेट. ओके ल
ओके. सो थ्यांक यू सो मच सर. अब हाम्रो नेक्स्ट सेसन चाहिँ अघि सरले भन्नुभएको जस्तै 17 सेप्टेम्बरमा हुन्छ. त्यसमा चाहिँ सरले यो द मोस्ट ब्युटिफुल म्याथमेटिकल फर्मुलाको बारेमा डिस्कसन गर्नुहुन्छ. So we'll see you in the next session. Okay. Thank you so much, Bhadra sir. Good night, everyone. Good night, sir.
Okay.
Good night. Thank you, sir.
Thank you, sir. Good night.
Thank you so much. Thank you, sir.
Good. Good.
Thank you so much, sir. Have a nice time.
Thank you, sir.